For those of you who,
In progress.
thanks, Andre. For those of you who don't know me, my name is Nathan Van Rumpt. I am a project manager for UBC Rocket, and in particular, I am working on the Whistler Blackcomb project, which is trying to go to space, basically. So today's presentation will be a little bit about my experience with the art of rocket engineering and a few of the lessons I've learned along the way about how to develop more high-level requirements with a system that's quite complex and has a lot of complex interworkings between its different subsystems, and it may not be obvious how to design within those constraints. This image on the screen here is actually from 2 years ago, November 2019, when we conducted our second engine test. And so at the end of the presentation, if we have a little bit of time, I do have both the engine test stand and the engine that we hot fired on that day here with me. I'm in the rocket space. I was doing some work in here earlier today, so if we have a little bit of time at the end, maybe we can look over some of those components and do a little bit of mechanical analysis as well. All right, I'm going to get started. So plan for today, we'll start with a little bit of some rocketry basics, talk a little bit about the highest level design objectives that our team at least is working under, and then how we go about turning those performance objectives into like a physical design. And then at the end, depending on what you guys want, we can do a bit of a analysis of something rocket related. So first off, a rocket engine is a high pressure gas. And there are two principles that create thrust from a rocket engine. The first one is a force and an area creates or a pressure and an area creates a force. And the second one is Newton's third law, which is basically if we throw stuff behind us really fast, we can go forwards really fast. And as it turns out, of these two, the Newton method is actually a lot more efficient at creating thrust. So there's some engineering that goes into trying to optimize it, but you want to maximize your exhaust velocity, even if it means your exhaust pressure goes down a little bit. The choked region right here basically just creates choked flow. And if you've taken a fluids course, you would know that as it expands in the nozzle, the exhaust velocity would increase and its pressure would decrease. But that's getting into a little bit of the weeds. And so all you really need to know is that if you can create a combustion in a small area, you can create thrust. And there are a couple of different types of rocket engines. There's monopropellants, bipropellants, solid propellants, and hybrids. We typically use the bipropellant engine just because it works the best for us. Both quantities are relatively readily available, and they're both stable on their own. Whereas if you have something like a monopropellant or a solid propellant, if you give it heat and it's just sitting there, it will combust, which is not good from a safety standpoint. And hybrids are something that we may look into at a later date, but again, similar issue with the solid propellant. And the second rocketry basic that you need to know in order to do any rocketry engineering is that you need to have your center of pressure behind your center of gravity. Your center of pressure is kind of like where all the aerodynamic forces converge. And so if you have your center of pressure behind your center of gravity, the rocket will just tend to orientate such that its direction of motion is when those two are aligned. And so if you start your rocket vertical, then it will tend to stay vertical because that's the direction that it's already going. And that's it. those are the two rocketry basics that you need to know in order to basically design anything. And literally every single rocket ever designed is simply based on these two principles. You need something that can hold a rocket engine and in a form that is aerodynamically stable. From small rockets to the largest rockets like Starship, if any of you are following what they're doing down in Texas, as long as you have those two principles, you have a rocket that can be quite effective. So moving on to some of the design objectives that our project is dealing with, we're part of a competition called the Base 11 Space Challenge. And the goal of this competition is to reach what is known as the Kármán line, which is kind of internationally recognized as the edge of space. And so our three objectives within the competition is that our rocket must reach 100 kilometers, which is a technical objective. It must be safe through all of the stages of operation, which is a safety objective, and it must follow all the rules of competition, which is a legal objective. And because safety and legal, while extremely important, are much more boring to talk about, I will be focusing on how to break down the first objective today. So the biggest question is, like, what does a rocket that reaches 100 kilometers look like? And while it may seem like a simple question, it has a very complex answer, and getting to that answer is quite complex. And the reason for that is everything on a rocket can be quite interconnected. And sometimes the equations can be circular. So say, for instance, you have some hypothetical rocket and you want to increase its thrust. Well, in order to do that, you would need to increase the flow rate of the propellant that you're using into the engine so that you can burn more propellant and get a higher thrust, which would give you a higher chamber pressure. But if you have a higher chamber pressure, you need to increase your tank pressure in order to compensate that, which means that now your tanks need to be thicker because they hold back a larger tank pressure. But now since they're thicker, they're also heavier, and so you need more thrust. And it's very, very easy to get caught in these circular loops, and not necessarily easy to break out of them. So there's a few ways to try and solve this. The first one is to look at other successful rocket designs and just try and get a general sense of what you should be looking for. The second one is to try and over-design everything with margins so that when you get into a scenario where, say, you need higher thrust, you don't actually need to redesign everything because you planned for higher thrust to begin with. And then the third way of doing it is to try and start with a good design and then optimize from there. I think I'm going to take a break for a second and just ask if anyone has any questions. All right, if not, I'll keep going. So kind of the only two rockets that I have found that are within our kind of similar category as us is the Attia 1, which was the first rocket that Rocket Lab launched. If you know of Rocket Lab, they are a New Zealand company that launches the Electron, which is the most prolific small satellite launcher currently operating. The rocket is fully carbon fiber and they do some really cool stuff, but I could get very into that, so I'm going to leave that for now. Their rocket was a two-stage. Its diameter was 0.15 meters, 6 meters tall, about 7 kilonewtons takeoff thrust. And the key point about it that's different than us is that they are a two-stage rocket and we are a one-stage. The second rocket that I have found is the Orion rocket, which was a early prototype sounding rocket, I believe designed by NASA, and similar kind of thing, 7 kilonewton takeoff thrust. Obviously much heavier because it was only one stage, as with us, rather than two-stage with the Attia rocket. And I'm just going to make a point in there. The reason why having 2 stages rather than 1 stage makes a difference is because you can do a very high impulse boost right at the beginning, burn a whole bunch of propellant, and then drop kind of all the dead weight of your rocket, and then just kind of coast with a much smaller section of it. So you have much less drag and have much less mass to carry with you. So you're able to be much more efficient. However, one of the rules of our competition is that you need to be a single stage rocket. So that is the condition that we're operating under. And this is our design. At a high level, we have a payload, avionics to control the rocket and get data and information, a recovery system, which is the difference between a missile and a rocket. Missiles, you don't tend to generally recover them, whereas rockets, you do want to. And then we have a pressurant tank, which pressurizes our oxidizer and our fuel, which is liquid oxygen and kerosene. And then we have our engine. And so using this kind of high level form factor, we can start to iron out what our actual design is going to look like in terms of rocket diameter, rocket length, what kind of thrust we're looking at, what kind of total rocket mass we're looking at, how long it's going to burn for, all that kind of stuff. So as I talked about earlier, there are 3 ways to try and solve the circularity conundrum. The first one was to look at other successful designs. And the second one is to try and over-design with margin. And that is where you figure out what your limit is and then either apply a safety factor to it or operate under a number of assumptions that are quite conservative and allow you to know that even in a worst case scenario, you are still going to be within physical constraints that allow your design to work. So these 2 pictures here are our composite carbon fiber fuel tank. This was a small scale prototype that we built last year. This tank burst at a lower pressure than we had designed it for. And so as such, we needed to increase the thickness of our tanks, which is the example that I talked about earlier, added more mass, but because we over-designed with margin, it doesn't affect the overall larger design too drastically because we incorporate that into it. There's a whole separate discussion about how much you can over-design, because if you over-design too much, now you're just overbuilding something and it is way more resource intensive and you're doing a lot of extra work that you don't need to be doing. So figuring out that balance is just as difficult and complex as everything else that I'm talking about today. And the third thing that you can do is to try and get a good design and then optimize from there. And the best way that we have found to do this is by finding the very few independent parameters in the rocket equations and defining a rocket based off of all of those. If you're curious, those 5 parameters that we have found is the burn time, chamber pressure, vehicle diameter, propellant mass flow rate, and the expansion area ratio in the engine. But in reality, it's not important as long as you have some variable parameters that you can change that changes your overall rocket. And then within those, you kind of have like a 5-dimensional equation where you put in these 5 parameters, and then your output from that is a actual rocket that you could design and fly. So the goal is to try and find what combination of those 5 parameters give you the best rocket. And that is a piece of software that we call Feynman. Feynman, I think, is quite cool. I've worked extensively with it, and if you want to talk about it more, I would be happy to. To kind of give you an idea of how these 5 parameters define a quote-unquote useful output. If you have something like burn time and propellant mass flow rate, that defines your total propellant mass by just multiplying them together, which then contributes to the loaded mass of the vehicle. You have something like your vehicle diameter that along with the amount of like the mass of kerosene and the volume of kerosene using some known constants can figure out your volume, and then the length of tanks that you need, which can then help contribute and isolate what vehicle length you have. And then chamber pressure, expansion area, similar things, specific impulse, and then along with propellant mass flow rate can define the thrust of your vehicle. And so what we do is change all of those 5 parameters and get an entire rocket out of it. And this is a bit of pseudocode, but this is basically what it does. It runs through every single possible combination of those 5 parameters, millions of possible rocket designs, runs a simple simulation with each and every one of them, and then tracks what the best design is. And then after it's finished running, you now have a vehicle design that you can make some CAD for and build some prototypes for and actually physically design and test. This is a graph that just kind of shows what some of those outputs look like. And the reason I have this in here is to show you that there is a very large span of rockets that are okay. Of each dot in the 4 chamber pressure, expansion area, burn time, flow rate, that was an input to the rocket system of equations, and then we got a rocket out of it. And so all of these were designs that could work. They would reach 100 kilometers altitude, but they weren't as good as they could be. And so the lowest mass of all of these is the optimal output, which is what we have kind of defined as our best rocket. The rocket that can reach 100 kilometers, but has the lowest mass possible. And the reason for that is just because it allows us to reach our design objective, but not have to build a 30-meter rocket that's the size of like a Falcon 1 or something. Although that is another way to do it, and some of our competitors in the competition are kind of taking that route, but again, won't get into that today. Well, first off, let me just ask if, does anyone have any questions at this point again?
I had a quick one. What is the x-axis?
Sorry, could you say that again, Meaty?
What is the x-axis in this diagram?
So the x-axis is just the iteration. So as it goes through this massive nested for loop, just the first one that it goes through would be number 1. The 10,000th one that it goes through would be number 10,000. So as you can see, chamber pressure is the first one that we go through. So this is how chamber pressure increases, like valid chamber pressure increases as we go through. And then you can start to see some correlations from this. If we have a lower chamber pressure, we generally aren't able to do as low of a burn time in order to have a valid parameter. We can't have as high of an expansion area ratio, and we can't have as high as a flow rate in order to get like a valid input out of that.
Nathan, I'm a bit surprised that you can't at least bound these parameters. There must be some, if you say, okay, I need the rocket to go 100 kilometers in height, there must be some limitations on amount of fuel or burn time. Is there some constraints that are not shown?
Yes. So the bounds that we applied to it for something like burn time is generally between 20 seconds and 45 seconds. Chamber pressure is like 600 pascals to, or 600,000 pascals to like 1.8 megapascals. So there's a very large range that we try and go through. And the reason for that is you could have a very small rocket that burns for a very short amount of time, has a super high thrust, and then just kind of coasts. Or you could have a very large rocket that goes a little bit slower, burns for a longer period of time, and those could both get to the same altitude. So trying to figure out what's the best between those is what Feynman is trying to do.
Yeah, that makes sense. Thank you. That makes sense. Thank you.
And there are also a lot of other constraints that we add in as well. So this check vehicle function that we have checks things like, is the amount of helium that would be required, you know, a reasonable amount that we could actually buy a composite pressure tank for? You know, is the required efficiency for this engine, you know, 99.5%? Is that something we can reasonably attain? Is the thrust of this engine 50 kilonewtons? And is that something that we could actually test? So we apply some filtering after it's designed each vehicle, but the gist of it is basically this. I know there's a lot of text on the screen, so I don't expect you to read all of it, but this is just an example output of what we get from Feynman. And the reason I have it here is to talk about some of the additional benefits we get by formatting our design process to be like this, that are specific to us being a student team. So one of our, or the most valuable resource for us as a student team is not actually money, it's time. All of our members are full-time students. They all have classes they need to do, and they all probably want a social life as well, although that's questionable for a lot of people because they just never leave, which isn't necessarily a problem. But being able to come up with a design in the shortest amount of time possible is what will allow us as a team to be successful. And I'm sure that carries over into the kind of general engineering field. But with Feynman, we can get a full, complete, defined rocket from this. And none of our members that are, say, experts in composite pressure vessel design need to worry about what diameter their tanks are going to be, or what types of end caps they're going to use, or anything like that. They just know, okay, these are our design objectives. We're going to create a composite pressure vessel that meets those technical design objectives, and then they can worry about how to manufacture it, how to test it, and not necessarily how to derive those requirements. And this is both good and bad, because good, it allows us to design things very quickly, but bad if a flaw in the code occurs, because that can throw everything else off. So a lot of our physical testing and design kind of comes full circle and goes back into Feynman to help improve it, so that it's not so much garbage in, garbage out, but if we are able to feed it better info as an input, it can give us a better, more accurate output. And so it's absolutely critical that everything is checked and verified, and then also compared with other successful designs, like I talked about earlier with the ATIA-1 rocket and the Orion rocket. Meaty asks, does Feynman need to take into account the rocket velocity profile, atmospheric density versus altitude, etc., to derive maximum dynamic pressure? So it does do that. We actually very recently spent a lot of time improving the aerodynamic code that Feynman uses, to get a kind of true aerodynamic profile of something like a rocket is very resource intensive. So what a lot of big aerospace companies, what they do is, you know, complex CFD analysis, lots of simulations, physical prototyping and testing. But when we're running this on a basically a home laptop, you aren't able to do that quickly, especially when you're trying to find the best solution out of millions of possible ones. So we use equations from a number of different like missile design textbooks and aerospace research materials that are a close, pretty good approximation of what you would likely see. And then after we get an output from Feynman, we need to do a lot of verification on what it's telling us to make sure that it's actually something reasonable. So that's when we do the complex CFD analysis, make sure that our drag's good enough, that our rocket is stable, center of pressure behind center of gravity, and do a more in-depth analysis with that just to, further verify it. And so using all of that, this is what we came up with for our current design. This is a 7-meter rocket. It is 0.4 meters in diameter. Takeoff thrust is 18 kilonewtons. Burns for about 35 seconds. We are in the process of building physical prototypes of sections of this and verifying that, it will work as we expect. But this is basically how we come full circle and design something. And then I also have a video here of the rocket top to bottom, just kind of give you a sense of how large it is. I'm also going to go back to the beginning and as it goes, kind of explain some sections of it. So up top here, we have our payload, which is a 3-unit CubeSat. UBC Rocket actually has its own payloads team that has been doing research with biological fuel cells and how they perform under different gravity environments. So a lot of our rockets in recent years have used that as our payload. Right below that, we have our avionics bay, which holds all of most of the data acquisition boards, communications, telemetry, sensors, that kind of stuff. Below that, we have our recovery bay, which holds our parachutes so that we are a rocket, not a missile. Below that, this large tank holds our high pressure helium, which we use to pressurize our tanks. These two valves are quite interesting. So we use a form of pressure control called dynamic pressure regulation, which is basically an on-off control that regulates the pressure in the tank. So we have a very high pressure helium upstream, and we want to keep our tanks downstream at a certain pressure. And so what we do is we rapidly open and close these valves and then basically adjust the PWM depending on if the tank pressure is lower than we want it to be, we increase it a little bit. If it's a little bit higher, then we decrease it a bit. And this gets back into the whole control theory that Andre was talking about yesterday, and how that is done with something like a pressurizing gas and a cryogenic liquid. It's very complex and a little bit above my pay grade, but we will be doing a lot more research into that later this summer when we get a physical prototype built. Meaty asks if the satellite achieves orbit. Does not. So the first privately funded non-government organization to achieve orbit was actually SpaceX in 2010. So achieving something like orbit is order of magnitude harder than even reaching space. So this whole competition that we're in is to try and be the first amateur rocketry university students to reach space with a liquid-fueled rocket. There are people who have done it before with solid rocket engines, but that is a lot more simple because you basically just have your entire rocket be a massive solid fuel rocket engine and you just light it and it goes up. But with liquid, you have to worry a lot more about stuff like your tanks, your plumbing, pressure regulation, carrying your pressure and gas with you, unless you're doing something like turbo pumps, which is even more complex. And then getting a liquid engine of our size range to work stably and not melt before it gets to the final altitude is really hard. And so that's another factor on top of everything that makes this more difficult. So yeah, a lot of people. Yeah, go ahead.
Oh, sorry. Just a question. You alluded to pumps. Why carry another tank of compressed gas as opposed to actually pumping fuel and oxidizer into the engine?
It's all about mass savings, basically. Mass savings and simplicity. So if you can design a pump assembly that is lighter than an equivalent tank and pressure regulation system, then it is obviously more in your favor in order to go with the pump system.
Okay.
But developing a pump system that is that small and that light is extremely complex, especially when you're dealing with something that's cryogenic, like liquid oxygen. So it's possible you could do it for, say, the kerosene that we use. That would be much simpler. But a cryogenic pump that can sustain the flow rates that we need and be lighter than equivalent, high pressure helium tank is quite difficult.
And there's no. Does anyone utilize what's the word I'm looking for? But sort of stagnation pressure of there as the rocket is punching through the air to provide some of that pressure, so you don't have to carry as big a compressed air tank.
They do something similar. The rockets that I know about that, what they do is they use actually the aerodynamic heating to sometimes boil off more oxygen and then kind of do autogeneous pressurization. That works better if you're using something like nitrous oxide, which can actually self-pressurize, and then you don't need to carry a pressurizing gas with you. But using propellants that allow you to take advantage of some of those things, generally they also have lower performance, and so you need more propellant, and then it goes back to just the mass savings of it. So if you need an extra, 100 kilograms of propellant using something like nitrous oxide versus liquid oxygen and kerosene, you might as well just use a helium tank with a pressure regulation system, because that'll be less than 100 kilograms.
Yeah. Cool, thanks.
So then we have our liquid oxygen tank, and then our composite carbon fiber tank. And then down here we have the good bits of the engine, our main oxidizer and fuel valve, and then our very large fins. And yeah, that's basically the rocket that we've come up with. So then after this, let's see, there we go. So once we have a design, we need to validate that the design actually meets the targets that we've determined. A number of ways to do this, and the principles that we follow come from this University of Calgary first-year engineering design document that I would actually highly recommend everyone reads at some point. I'm going to put it in the chat here. It's all about ways that you can verify that something works the way you intend it to. And the 5 ways is demonstration, inspection, analysis, similarity, and testing. So demonstration is operating in the exact or representative scenario. Inspection is like measurements or like otherwise confirming that it meets the design. Analysis is can be very in-depth. You have off-the-shelf tools like SolidWorks, ANSYS. For rocketry, you have RAS-Aero and OpenRocket. And then you also have internally developed tools that you can use, which for us is a MATLAB force model, which you can see an output here on the right of that just tells us what forces we will see at different points on the rocket. And then we also have a Monte Carlo simulation that changes certain things about the rocket to see how that affects our flight trajectory. And then we use something like that to get approval from the FAA, so that, even in a worst case scenario, we can tell them that we will still be landing within the zone that they allow us to fly in. Similarities, comparison with other known good designs, which goes back to the other two rockets I talked about. And then my favorite thing is testing. So that's stuff like doing engine hot fires, tank burst tests, drop testing of parachutes, and like structural stress testing. That was something I was very involved in my first year, and something I'm quite passionate about. But yeah, design validation is just as difficult and complex as coming up with the design in the first place, and could certainly be its own separate talk if somebody wanted to do that. And to finish this off, I have a video because I can't talk about rockets without showing a rocket engine test. So I'm going to play this. Might be a headphone warning. So enjoy. And that's it for me. Thank you, everyone. Does anyone have any questions?
Well done, Nathan. Well done, Nathan. That was excellent. I have a bunch of questions. Well, I have one in particular. If I can start where other people are seeing theirs. Materials. So you've talked about a carbon fiber tank. What materials are you using throughout the rocket?
Good question. Let's see if I go back to here. Our nose cone is going to be carbon fiber, and then we're actually going to have an ablative coating on it. So we want the carbon fiber because it has a very, very high stiffness to mass ratio, so it can sustain a lot of force, but it's not so great at high temperature. So we cover it with a sacrificial coating that, as it heats up, it doesn't burn, but it kind of forms like a protective layer, and then the protective layer falls off and kind of carries a lot of that heat with it. And then
what's that material? What's that material?
Pardon?
What's the ablative coating made of? What's the ablative coating made of?
So we're actually doing some ablative testing right now to figure out what we will actually be using. There's a couple like known things that you can use. So MDF is actually a pretty good ablative. Cork is also an ablative, and then there's more exotic ones that you can use, like carbon nanotubes and graphite and other stuff like that. So just basically any material that has low thermal conductivity that will undergo an energetic reaction and then fall away.
Okay.
After our nose cone, we have our tank sections. A lot of our tank sections, again, are made of carbon fiber because of the high stiffness to mass ratio. We also use a lot of aluminum for structural pieces. And for our liquid oxygen tank, we are making it out of stainless steel. Reason we're using stainless steel is because under cryogenic conditions, stainless steel actually gets stronger. And it's also a lot easier to weld than aluminum. And since we're welding and making our own tanks, anything that makes the process easier is a big win for us. And then we have our carbon fiber tank, which has an aluminum top and bottom ring so that we can clamp onto it. Tristan asked, cryogenic is sub-zero conditions. Cryogenic is generally like negative 200 degrees Celsius and lower. Basically kind of the range at which, liquid nitrogen, liquid oxygen, liquid helium exist, kind of these normal gases that are normally gas. When you cool them cold enough, they become a liquid. So very, very cold, but yes. And then our engine is made of combination of mild steel, aluminum, stainless steel. And then our fins are a milled aluminum frame, and then we have like a low density foam that we stick on the inside so that they're still quite strong, or they have a lot of like resistance to compression. And then we put carbon fiber over the edges of it to give it an aerodynamic covering.
Right. Yeah, I was actually wondering about that. Whether you use I was actually wondering about that for your tanks. Whether you use just solid carbon those fiber techniques for your tanks, like is it just solid carbon fiber, or do you layer it with?
Yeah, no, it's just solid carbon fiber. So we use a pre-preg carbon fiber, which basically means that it has the epoxy already in it in the optimal strength to mass ratio. And that's just because you have your carbon fiber, but then you want an epoxy to actually hold it together, and getting the right proportions of that is difficult. So you just buy it in the right proportions to begin with. And so what we do is we basically roll it up over a cylinder, generally 4 to 5 layers of carbon fiber. And then the end caps we make in a mold, similar process. And then we just slip the end caps inside of this tube and epoxy it in place.
Cool, thank you. Well, thank you.
I wanted to ask, how accurate is Feynman? I'm guessing when you do your simulations, and I'm guessing you do force testing and stuff. How close on the actual rocket when it's done? How close are like the Feynman's predictions to?
Great question. So Feynman for us is a tool. Obviously, it doesn't give us the final design. We've kind of figured that it will get us within 10% of our final design. And it incorporates margin into that as well. So like, for instance, it applies a 10% safety factor for mass onto all the structural components of the rocket. So even if we're much heavier than we think we're going to be, design will still work. And we also have like miscellaneous mass that we can pull from. So that's, I think we have 10 kilograms, give or take, that we have as like a miscellaneous mass addition. So if we're not accounting for other things like, I don't know, something else, we can pull from that miscellaneous mass so that we, again, are designing with margin. Great question. So we got about 1 second of data, but there's a lot that comes from that as well. So not only was it just like a 1 second test, it also verified that our test stand works, which allows us to do longer tests and stuff. We, for this test that I showed you guys, achieved the chamber pressure that we were looking for and the thrust that we were looking for, which validated the engine and the injector design, and a couple other kinds of things. It was just kind of like a verification test. This summer and into next year, we're going to be doing a lot more tests that are longer duration, that will be able to get information about combustion stability, long-term effects on the engine, how our thermal gradient shows up, like if we have any sort of hot spots along the engine, and other stuff kind of like that. Great question. So we have 2 systems on the test stand. I don't know off the top of my head what their speed is. I could probably find it somewhere. But we have a industrial PLC as our control system that controls all of our valves and stuff, and then gets enough of the sensor input that it can control and run the test stand. And then we also have a lab jack that we use for high-speed data logging, and then all the sensors just go to that, and it's just constantly reading data. Sorry, I don't know off the top of my head what their relative speeds are, but effectively as fast as we could, as we are able to sample the sensors and stuff. You know, it kind of does feel like Mythbusters sometimes.
Nathan, who wrote Feynman?
So that
who
was
wrote
actually Simon Bambi. He wrote.
Okay.
Yeah, so it was kind of like a bit of legacy code that was given to me, but I have been the one maintaining and running it for over a year now.
There's astonishing similarity between that design process. And even Feynman's visual sense, the output of Feynman's predictions there. What we use for designing DNA panels. What we use for designing DNA panels. It's a recursive design problem. And I think it's the same problem. It's a recursive design problem. So it's not something you can solve analytically. We get the same thing. We have a number of and we get the same thing. We have a number of all the DNA probes, variables which are really the sequences of all the DNA probes, that we use to target, say, a lung cancer gene panel. And what's interesting to me there that I wonder if what's interesting to me there that I wonder if would apply to you is that we had a code very I suspect a lot like Feynman, where it was just doing analytical calculations, thermodynamics calculations, different versions of the panel, and producing 1,000 different versions of the panel that we would then at some point replaced it with machine learning. And we then at some point replaced it with a machine learning algorithm, successful, and started feeding it that had worked, successful panels that had within weeks, and within weeks, better than the original analytical. It started to do better than the original analytical. I'm wondering if algorithm. You take all the successful rockets that have been made, and you take all the successful rockets that have been made, and Feynman, make a machine learning version of Feynman.
I have tried that, or something similar. I tried to do a gradient descent version of Feynman, which is kind of machine learning. For those of you who don't know, gradient descent is basically you have your function and you have a starting place, and what you do is you take a small step in every single direction that you have for your parameters. So for something like Feynman, you have like a 5-dimensional space that you can move around in. So it takes a small step in either of those and basically checks which direction would improve its output the most, and then moves in that direction, does the same sort of small step check, and then continues doing that until it finds a minimum. The issue that I found with it is that for each of those small steps that you want to make, you have to fully redesign and build and simulate another rocket to get an output. And so in order to take one small step, you have to do 5 or 10 other rockets. So in some cases, it's almost faster to just do the nested for loop method, or nested for loop method that I showed earlier.
Yeah. I mean, also a gradient descent. I don't know. Yeah. I mean, also a gradient descent. I don't know. Medium might have something to say here, but I'm not sure that I would classify it as machine learning. It does also get stuck in local energy minima. It does also get stuck in local energy minima.
Which again runs into that thing that I talked about earlier, how you can have a rocket that is very small, very fast, that meets the same objectives as something that is larger and slower. And so figuring out the best between all of those local minimums is difficult as well. The proper machine learning code, I think, will actually run a lot faster than that, because it's not at all doing the same thing. Anyways, that's super cool. A lot of fine details, yes. I'm glossing over the complexity here. Chase asks, how did you decide on weights for output parameters for the gradient descent when you were trying it out? For that, I just kind of used the relative steps that we use. So within something like chamber pressure, for instance, the steps that we try at are like 100,000 Pascal increments. or something like that. And then our, for instance, propellant mass flow rate, we sample at every 0.25 kilograms per second. And so I just put those relative weights as equal to each other when I did like the small step. That way it was also sampling at the same kind of locations initially as the kind of linear method. And so I could run a gradient descent version and a linear method at the same time and confirm that they got to the same optimal solution. But again, was running into issues with local minimums and actually finding the global minimum. Tristan asked, how do you convince yourself that you've achieved the global minimum once you're in a single one? So there is a couple techniques that I found to do that. That's where you run the gradient descent many, many times. So you start from a random point, do gradient descent until you find a local minimum, and then go to another random point. And then once you start to converge to the same minimum, or you get kind of a relative map of a number of minimums, you can choose the lowest one. But again, it's a very complex art that I am certainly not an expert in. Tristan also asked, format it as a annealing problem. Spend more time looking. Maybe you can format or ask that a different way, Tristan. I'm not sure I understand. Yeah. Does anyone have any other questions?
I'd love to see. If we've got maybe 3 or 4 minutes here. If you've got a way to show us some of the stuff, that'd be brilliant.
All right. I will get Zoom open on my phone.
And if people have to drop off for class, obviously, we are recording this, I believe. So.
Here we go.
Recording in progress.
Just go over here. Okay. I think I need to mute myself. You guys able to hear me?
Yes, yeah, great. That's awesome.
So this is our test stand. Got the PLC up here. I also wanted to point this out to people. If you look down here, let me change. You may notice that's a blue pill. So we actually use a blue pill in our igniter system to run. And that's how we start our engines, which is pretty sweet. This is some of the engine components. This was the engine that I showed you in the video. We actually blew this up last time we engine tested. Again, a whole nother conversation if anyone wants to get into that. So a rocket engine is basically just a fancy pipe that has like an injector attached to it that injects propellants into. And then igniter is up here. Nozzle is right here, and that constricts the flow. And then this is the injector that we use. Very simple design. Fuel comes in the one side, liquid oxygen goes down the middle. And so the fuel comes out as a ring around the pintle, and then these little holes right here are how we inject liquid oxygen in, and that creates turbulent flow inside the chamber and allows us to get good mixing. And so once those are all assembled together, they come over here and sit on our test stand like this. Load cell goes right there, and it pushes all the force into the load cell. And it gets its kerosene or its fuel from this hose right here, and the liquid oxygen from the other side. Hoses come back here, go through a valve so that we can control the amount of propellants that we want to flow. And that comes from a tank over here, which you may notice is just a scuba tank. And similar thing on the liquid oxygen side. Except over here, we have 2 tanks because we need more liquid oxygen than we do kerosene. And then up here, these hoses or this piping comes up and around, and then through this valve, which opens the pressure line from these tanks here. And that's pretty much it. It's relatively simple system, I think.
Super cool, Nathan. Nathan, thank you. I see it's 1:30. I don't want to make people late for their next class. But that was amazing. Thanks again so much. And yeah, I'll see you all tomorrow.
Awesome. Thanks, everyone.
Yeah. Thanks, Nathan.